Hello everybody, in this video we're going to talk about what is a day. So how did the humans define what a day is? I'm sure all of you have ideas and you think you might know what a day is, so hopefully when you go through this video you'll be a little bit surprised. For this content, you really should have already gone through Unit 1, Part 3, the diurnal day, or diurnal motions of the Earth. We're going to be talking about the motions of the Earth, and of course, the rotation of the Earth is going to be something that helps us define the day. This video is also going to have a Google form associated with it, so you can go through and answer the questions as you go along. And the way I'll do it is I'll present the question, you'll pause the video, you'll answer the question on the Google form. It's an optional thing that you can do, but it should make this video a little bit more interactive to really reinforce some concepts. And then once you answer the question once you come back to the video, the next slide that I present will give you the answer. All right, so if I'm talking about slides, I should be sharing some slides. So let's go ahead and bring up my slides. All right, so here we go. A big question. Seems very, very simple. What is a day? How have humans defined our 24-hour day? Why do we have 24 hours? That's more of a question for philosophy and history. But we all live in a 24-hour day. So we have a 12-hour clock or a 24-hour clock that we live by, but we know that we define, so humans have just defined that there are 24 of these things called hours in a day. But really, that doesn't address what is one full day. And here we have a couple of ways. We have sort of the way that you probably heard about this in your science classes through elementary school and middle school and high school. So is a day defined by one full 360-degree rotation of the Earth, so one complete spin of the Earth? Or is the day defined by noon? And that assumes that you have already reviewed and know what solar noon is. Is the day defined by marking when noon is one day and then waiting for the next noon? So from solar noon to solar noon. And good to put the other option, or are these two ideas the same thing? Is one 360-degree rotation, is that the same as our noon to noon time? So go ahead and pause the video and give this question a stab on the Google form. And I will go ahead and do my rotation over here one more time. Seems like a good amount of time to pause between. All right, so turns out that both of those options defined a day. We have two different types of days. The noon to noon 24-hour day, the day that we live on, the day that our clocks keep time on. So every time you check what time it is, you are looking at the 24-hour day. That 24-hour day is the one that marks noon to the next noon. So our 24-hour day is the one that's defined by solar noon. And just a reminder, in case you haven't reviewed those slides that I asked you to before watching this video, solar noon is defined as the time that the sun, solar noon is defined as the time when you go outside and you watch the sun and it reaches its highest altitude, that point where it's crossing the meridian, what we call culmination. At that point when the sun is crossing the meridian, that defines noon, solar noon. So you wait for the sun to be crossing the meridian, you wait until the sun comes back around, rises in the east, reaches the meridian again, and you go from one noon to another noon. That's 24 hours. So we just call that one day and divide it into 24 hours. Since this day is defined by the position of the sun, we're using the sun to define our day, define time here. We call this day, this noon to noon day, our solar day, the day defined by the sun. All right, how long is this one? This one is 24 hours. But there's that other option. You probably remember, and you maybe feel like you got lied to a little bit, that 360-degree rotation of the Earth is what a day is. Well, that is a different type of day. The full 360-degree rotation, one full spin around, 360 degrees, of the Earth defines a different day. So that 360-degree, one full rotation day is what we call the sidereal day. I know that's probably a new term, sidereal, but it's a good one to go ahead and start putting into your brain because it's going to come up a lot in this class. So sidereal it's referring to sidereus, the Latin. So sidereus in Latin means pertaining to the stars. So it's what we're going to be using the day that's defined by not the sun, but where the stars are in the sky. But pretty much an effective definition for sidereal is that every time you hear about a sidereal day, a sidereal period of some kind, some passage of time that has sidereal associated with it, then what you're talking about is 360 degrees of rotation or revolution of something. So 360 degrees of rotation, spinning around, or 360 degrees of revolution, orbiting around. All right, so this one is a little bit different. The full 360-degree rotation day, the sidereal day, is probably going to come as a surprise to you. This is not 24 hours long. How long does it take the Earth to rotate exactly one time? 23 hours and 56 minutes. And I want to go ahead and show you a little bit more, since this is a new concept, what the sidereal day is and how we are actually using the stars to measure it by. All right, so hopefully when we review my slides, my textbook slides, you actually go into presenter mode like I am now, so you can see the animations. If not, you'll see that it is very advantageous. This slide is a good demonstration of one of my animations. So here I have the sun with the orbit of the Earth on it. But we have to remember that when we consider the stars, we'll go back to our football field where we had the sun in Neyland Stadium. The nearest neighboring star was in Washington, D.C. The stars are really, 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 really far away, which means that the orbit of the Earth is tiny compared to that distance. It's just on the 3.3 yard line compared, so 3.3 yards compared to the 500 miles. That's a tiny, tiny, tiny orbit in perspective of how far away the stars are. So we can't even really see Earth's orbit if we were to zoom out and be able to see even the nearest star or just the stars in general and our sun with Earth's orbit. So now I can go ahead and put the Earth there, ridiculously too large. But for us, whenever we're considering where the stars appear in our sky, in our local sky, so here I have my horizon drawn. I know that the planet is rotating around counterclockwise, because I've marked the North Pole. So this defines east, and there we have west. And in the middle, right here, we're going to put the meridian. So we're going to look for a meridian crossing to the next meridian crossing. We don't have to worry about the orbit of the Earth, because it's so small, that motion doesn't really register. So let's just consider the rotation of the Earth. And it just spins around exactly once. And now we can see that that star would have moved from meridian to the next time it crosses the meridian. And that is our sidereal day, our day where our star, you find your favorite star, put it on the meridian, wait for it to be on the meridian, go out the next night, and when it's crossing the meridian again, you have marked one full rotation of the Earth, our sidereal day. So our solar day was the sun going from meridian crossing to the next meridian crossing. The sidereal day is a star going from meridian crossing to the next meridian crossing. And it's not the same amount of time. There's a 4-minute difference. All right, so we have the two types of days. We have our solar day and our sidereal day. Just to go back to our sidereal day, we have our sidereal day, 23 hours, 56 minutes. Our solar day, 24 hours. There's that 4-minute difference. And the rest of this video, other than the Stellarium demonstration at the end, is going to be explaining what causes that 4-minute difference, why we have 2 days. Why is the sidereal day 4 minutes shorter than our solar day? But before we do that, I want to go ahead and make sure that you're starting to associate sidereal day and solar day with the appropriate concept. So I have a question for you. So after I finish saying this question, hit pause, go to the Google form, and attempt to answer questions 2 and 3 here. So the setup is you go outside at night and you wait for your favorite star, what I was just talking about, to cross the meridian so it's at its culmination point. The highest it's going to be is due south and it's on the meridian. So you mark that star, it's on the meridian, And you're like, okay, good. You figure out exactly how you can find that the next night. So you go, you get some rest, you come out the next night, and you watch that star until it crosses the meridian again. So you watched your favorite star cross the meridian, and then you waited until you saw it cross the meridian again. So the question number 2 is when it crosses the meridian on the second night, sorry about the typo there, how much time has passed from when it crossed it on the previous night? In hours and minutes. And then the follow-up question to that, is this the definition of the solar day or the sidereal day? Pause video. Okay, I'll assume that you're back now. So when we're talking about a star, we're defining a day by a star going from meridian crossing to the next meridian crossing. That's our sidereal day, our star day, and we mark one full 360-degree rotation of the Earth. So the answer to 2 was 23 hours and 56 minutes. The answer to 3 was the sidereal day. Now let's get to explaining the 4-minute difference. So the sidereal day, and yes, the sidereal day should be in bold blue there. Sorry, I didn't highlight that. The sidereal day is determined only by the rotation of the Earth, because the stars are so far away that we can ignore the orbit, the revolution, Earth's orbital motion around the sun. So the sidereal day is only determined by the rotation of the Earth. The solar day, however, the sun is a lot closer, so the orbit of Earth is pretty big compared to the Earth-Sun distance. In fact, the orbit of the Earth, the radius of the circle is the Earth-Sun distance, 1 astronomical unit. So that's a pretty big circle compared to how far away the sun is. So we have to account for not only the rotation of the Earth, but also the Earth's motion around the sun, the revolution of the Earth around the sun. Orbital motion is called revolution. Rotational motion is called rotation. Spinning motion is rotation. Orbiting motion is revolution. In the solar day, we have to account for both. And it's my job now to convince you and show you how this all works out. All right. The first thing we should do is ask ourselves is, well, how much is the Earth going to orbit in one sidereal day? How far along its path around the sun will the Earth go in one sidereal day? I can go ahead and crunch the numbers. Notice I put this in green because I don't expect you to crunch the numbers. I know to orbit all the way around, that'd be 350 degrees of revolution. And I know that it takes 365.25 days, or how many days are in 1 year. So 360 divided by 365.25 equals about 0.985. That's approximately 1 degree per day. So from night to night, the Earth will move 1 degree in its orbit. Not very much, just a little bit less than 1 degree. To actually understand this difference, instead of just playing with a tiny motion of 1 degree, I'm going to really speed up the Earth and consider an extreme scenario where instead of just moving 1 degree per day, I'm going to have the Earth move a eighth of the way around the sun, a full 45 degrees. So time is moving 45 times faster in this extreme case. And that's just so we can really see this difference. So we have the Earth, and then it's orbiting super fast in this extreme case. So it'll go all the way around the sun in 8 days. So 1 day later, it'll have moved this far. What have I drawn on here? So I have the rotation of the Earth. I have the night side and the day side of the Earth marked. I have the middle of the day marked. Notice that's right here in the middle of the day. And this would be the meridian as well. So the sun is crossing the meridian. So this arrow marks solar noon. So if you're right here where this arrow is, you are at the time of solar noon on Earth. And what we're going to do is we're going to wait for 1 sidereal day later, let the Earth do 1 full 360-degree rotation, but we also are going to have it orbiting simultaneously. So my question to you, this is not a Google form question, is this right here in one sidereal day later, is this arrow right here at solar noon? Another way to think about this is, does this arrow point directly at the sun? Obviously, it doesn't. You can even see with the shading here that no, it is not in the middle of the day. This is not a solar noon. The sun would not be on the meridian. So a full sidereal day later, and we're not at noon. Clearly, there has to be some difference. All right. So let's just go ahead and look at that a little bit. So in one sidereal day, we get full 360 degrees of rotation. But we also have to account for the orbital motion of the Earth. So we might want to ask ourselves, how much does it need to rotate to get, how much extra rotation does it need to do to get back to solar noon? And sorry, I couldn't animate the day-night side there. So we see that I have to rotate a little bit more, so it's going to take more time. The solar day will be longer than the sidereal day. But we need to know how much more is it going to take to rotate the extra bit. And in this case, it moves 45 degrees this way, so I'll need to rotate 45 more degrees this way in this extreme scenario. So one more time, it's going to have to rotate an extra 45 degrees to hit the next solar day. So the sidereal day plus extra rotation to get to the solar day. Clearly, the sidereal day is going to be shorter than the solar day. Okay, so this is an extreme scenario, just so you can see that this clearly isn't pointing at the sun. So this is not, it is clearly not at noon. It'd be really, really hard to see if I only move the Earth 1 degree. I'll do my best with that though, and what I'm going to do is I'm going to zoom in, and I'm going to play a little bit fast, and loose. This is more than 1 degree, but let's just pretend this is 1 degree. So this is the real scenario. This is the one that we live in. So in 1 day, the Earth will move approximately 1 degree. Here I have a line that would point to the stars, which would be way upstream. And this line right here points towards the sun. So this would mark solar noon. In one sidereal day, you spin around and point back to the star. But it needs to do that little bit of extra rotation we saw in the previous slide. But since it moved 1 degree in its orbit, 1 degree of revolution, it's going to need to rotate 1 extra degree. So we need to ask ourselves, how long will it take to go from the sidereal day to rotate that 1 extra degree to get to the next noon, to get to the full solar day? So how long will it take the Earth to rotate 1 degree? And again, this math is in green. I don't expect you to reproduce this. So let me go ahead and walk through it. So there are 360 degrees of revolution spinning around. And it's doing 1 full revolution in 1 sidereal day in 23 hours, or 23.93 hours, so 56 minutes. And you can crunch those numbers. It comes out to about 360 divided by 24, which is 15 degrees per hour. So the Earth will rotate, in 1 hour, it will rotate 15 degrees. So that way, in 22 hours and 56 minutes, it rotates the full 360 degrees. Now let's go ahead and figure out that how many minutes it takes for a single degree. I'll go ahead and do that. We have 15 degrees per hour, and I know that there are 60 minutes in 1 hour. And now I can go ahead and cancel out my hours, so I can get degrees per minute. And I can go ahead and 15, 60, or make that a 1, make that a 4, 1 degree per 4 minutes. So the Earth rotates 1 degree per 4 minutes. In 4 minutes, the Earth will rotate that 1 extra degree. So it takes the full 23 hours and 56 minutes for the Earth to rotate exactly 1 time, but it also moved in its orbit that 1 extra degree, meaning it needs to rotate 1 extra degree to get to the next solar noon. And how long does it take the Earth to rotate that 1 extra degree? 4 minutes. There's our 4 minutes right there. That is why that the sidereal day is 4 minutes shorter than our solar day. So how did we actually determine that Earth's rotational period, its sidereal day, is 23 hours and 56 minutes? Well, we originally marked time by noon to noon. We defined the solar day, and we just set that to be 24 hours. And then through observations and things like that, we realized that there are differences between the solar day and the sidereal day. And there's a 4-minute difference. So to actually calculate the sidereal day, we have to take the 24-hour solar day and we subtract off the 4 minutes to determine that the sidereal day, the full rotational period of the Earth, is 23 hours and 56 minutes long. There we go. We know the difference between the solar day and the sidereal day. We'll do it. So another concept check. So 2 different questions here. I'll read the questions and then I'll let you pause the video. And hopefully you can get these. These are multiple select. You can select no choices, 1 choice, or both choices. So the length of the sidereal day is determined by which of the following? So is the sidereal day determined by the rotation of the Earth, the revolution of the Earth, or the rotation and the revolution of the Earth? And then the same question for the solar day. The length of the solar day is determined by which of the following? Is it the rotation of the Earth alone? Is it the revolution of the Earth alone? Or is it the rotation and revolution of the Earth? So I'll give you a minute to go to the Google form before I reveal the answer. So go ahead and hit pause. And now we're back. So let's see how you did. So the sidereal day depends only on the rotation of the Earth. It's defined by the rotation of the Earth. 360 degrees of rotation, and yes, I like sitting in my chair. The solar day is a little bit longer because we have to account for the rotation of the Earth, the 23 hours and 56 minutes it takes to rotate exactly 1 time, but also move in its orbit by 1 degree, which means it needs to rotate an extra 1 degree to get to noon, so we got to account for that extra 4 minutes. So the rotation and the revolution that need to be accounted for. And now I want to go ahead. I know this is one of the trickiest concepts that we've covered so far in this class, and I know students have trouble with it over and over, so I want to give you some example questions and some answers. This is the kind of question you might expect on a quiz or an exam. So let me read the question, set up the scenario, fully describe it, and then take your stab at it on the Google form, and then I'll reveal the answer. So consider the following 2 scenarios. Our normal scenario, the one that we live in right now, where the Earth orbits at about 1 degree per day. So our year is 365.25 days. And then consider a different scenario, an imaginary Earth, where it orbits 2 times faster. So now it's orbiting the sun faster. And if it's orbiting 2 times faster, that means our year would be 182.5 days. So it's orbiting the sun twice as fast. Let's assume that we're going to keep the rotation period the same. So the sidereal day is still 23 hours and 56 minutes. But now we have sped up the Earth. So instead of orbiting 1 degree per day, it's going twice that. It's orbiting about 2 degrees per day. So in this new scenario, compared to what our solar day currently is, would our solar day compared to our current solar day be longer, shorter, or would it be the same amount of time? So is the time difference, is it going to be 4 minutes, the same, or is it going to be less than 4 or more than 4? The time difference between the solar day and the sidereal day. So go ahead and hit pause, try to answer that question, and then I will talk through the answer, and I'll give you one more example before I do my Solarian demonstration. Now it's time for the answer. In this case, it would be longer. Our solar day would become longer than it currently is. Why would it be longer? And the way I always like to think about this is, okay, 1 full rotation, 1 sidereal day, 23 hours and 56 minutes, and then I want to ask myself, how much more does it have to rotate? I'm keeping the rotation the same, so I'm not changing how fast this rotation is happening. And in this one, it needs to rotate 2 degrees, which is more than 1 degree. So it's going to take it longer to rotate that 2 degrees to offset its orbital motion, to account for its orbital motion. So it would, in 4 minutes, so 24 hours, it would rotate 1 degree, and then 24 hours and 4 minutes, it would rotate another one. So here, our solar day would be 8 minutes longer. Okay, hopefully everybody was on board with that one. Let's consider the opposite scenario. So now we'll have our normal scenario, but instead of speeding up Earth, I'm going to slow Earth's orbit down. So it's going to orbit the sun half as fast, which would mean that the orbit, the orbital period, how long a year would be longer. So it's orbiting half as fast, which is twice as long to get all the way around the sun. So it would be 730.5 days long. Instead of orbiting 1 degree per day, it's going to orbit a half a degree per day. So in this new scenario, this Earth is orbiting slower scenario, would our solar day, compared to what it is currently, be longer, shorter, or would it stay the same? And again, assuming the sidereal day is still 23 hours and 56 minutes. Go ahead and take your stab on that. And I'll see you when you get back from the Google form. All right, let's see if you are correct. So in this case, oops. Oh, crap. Apologies, everybody. Let me go ahead and fix that mistake right there. Oops. Nothing like some real-time fixing. Okay, so in this scenario, the solar day would be shorter instead of longer. Why would it be shorter instead of longer? Well, let's go back to here, it rotated 1 degree. So it would have to do 1 extra degree, it would have to do 1 extra degree of rotation. This would take about 4 minutes. Here, it only orbited half a degree, so it's only going to have to do half a degree of rotation. And it's only a half a degree of rotation, so it's just spinning at the same speed, takes a shorter amount of time. So the solar day, our noon to noon time, would be closer to what our sidereal day is. And again, I apologize for the mistake there. Whenever I reformatted things, apparently I popped the box up just the right amount, so it was circling longer. Hopefully nobody got too confused by that, because I did fix it in real time. I apologize for that. But what I want to do is I want to show you what this actually looks like on Sidereal. So I'm going to switch my display and show you what a sidereal day and a solar day look like on Sidereal. All right, let's go to full screen because it makes everything easier on mine. Good. All right, let's orient ourselves to where we are. So I am at tonight at 11 p.m. I've frozen time, so we don't have to worry about the seconds ticking away. And I've put up the constellation figures just to draw your eye. And hey, we even have 2 planets that are visible. So if you want to see 2 planets, it's a clear night, go out, and the really bright one will be Jupiter, and then you can also see Saturn right near it. So what I'm going to do is I want you to watch this timer and see how the sky changes. And I'll tell you what I'm doing. So I'm going to advance time by 1 solar day. And the stars have shifted. Another solar day, another solar day, and you can see down here that the date is ticking up. So again, plus solar day, plus solar day, plus solar day, plus solar day, plus solar day. Huh, interesting. So we saw that there's a time difference. The stars are moving from one solar day to the next day, and they seem to be moving consistently to the west. All right, so now I'm going to advance time not by 1 solar day, but by 1 sidereal day. And I'll tell you when I advance time. So keep your eye, keep your eye right down here at the time and the date. So advancing time by 1 sidereal day, another sidereal day. Notice that the time is changing by how much? about 4 minutes. What's happening with the stars? The stars are just sitting there. They aren't changing. This star is on the meridian 1 sidereal day later. So that went up. That changed by 23 hours and 56 minutes. And the star is still on the meridian. This is why we call it the sidereal day, the day defined by stars. And just a little preview of, we're going to have to eventually explain planetary motion. All right, so let's go ahead and back this towards noon. So now we have the sun on the meridian. And what I'm going to do is I'm going to advance time by 1 solar day. And the sun pretty much stays right there on the meridian. Now I'll advance time by 1 sidereal day. And the star stays still. But the sun is not at the meridian. In fact, let me go back to sun being at the meridian. I'm moving time backwards right now. So that's pretty close to the sun being on the meridian. And I'm going to advance time by 1 sidereal day. And notice that the sun is in the eastern part of the sky. So 1 sidereal day later, it'd still be rising. It hasn't yet reached its culmination. It hasn't done its meridian crossing. I gotta wait for 1, 2, 3, 4 minutes for it to reach the next solar noon. All right, so I wanted to show you how this could actually play out with Sidereal. Hopefully this long video was an educational one, and the Google form really helped. I would enjoy getting some feedback on the Google form if that kind of interaction is good. It did take a lot of extra time to create, but I think it was worth it. Thanks for tuning in.